Hi there, grade 12s, and welcome to our lesson on calculus application. My name's Tamlin, and today what I'm going to be doing with you is taking all the basics that we've learnt about calculus, being our differentiational rules, our first principles. We've learnt about tangents and finding equations of tangents. And we're going to take all of those things and we're now going to put them into application-based questions, okay? Which forms a really big part of your calculus paper, and it's important that we really understand how it all works, okay? Right, we're going to start by having a look at our calculus application checklist, okay? What we've got on our on our checklist is we're going to have a look at things like interpreting graphs using principles of differentiation. We are going to have a look at drawing and sketching our cubic graphs. We are going to have a look at, and this is always a bit of a tricky one, using the graph of the derivative to answer questions about the cubic function. And lastly, we're going to have a look at solving problems involving maximum and minimum. Okay, these are all really important concepts in calculus, and really if we just go back to the basics of what we know about calculus, generally they're pretty fun and they're not too bad to work out. Right, before we get going, what I want to just start off by confirming is that we all completely understand what the concept of a derivative actually is, okay? We start using this word derivative so much in calculus that I think we tend to forget what it is that we're actually doing when we're working with this derivative, okay? So, grade 12s, what we need to always remember before we do anything is that when we are working with a derivative, what you are doing is you are finding the gradients. And remember, another way of referring to gradients is your rate of change. We're finding the gradients at 1 point. And another way I could phrase that is we're finding the gradient of a tangent. Remember, a tangent and a function connect each other at 1 point. So when we're working with the derivative, we are finding the rate of change, we're finding the gradient at 1 point. Okay, now that's really important to just remember it, keep it clear in your head, so that when we are interpreting all these questions, we can always go back to that basic rule of a derivative. Okay, right, let's have a look at our checklist. I'm actually going to begin over here. We are going to have a look at sketching a cubic function. Okay, this is generally always going to be in your paper, and you can be guaranteed it's worth a fair bit of marks. So if we just deal with it in a structured and careful way, the marks are generally not too difficult to get. Right, where do we start when we are sketching a cubic graph? Okay, we can break this down into steps, grade 12, and by doing that, it generally makes the whole process quite a lot easier. Let's start with step 1 of our process of sketching a cubic graph. Step 1 is let's decide what shape the cubic graph is actually going to be here. I can see that my equation as it's been given to me is f of x is equal to 2x cubed minus 6x minus 4. Okay, what we are able to see from here is that this a value in front of our x cubed is positive. And because that's positive, I know that my cubic graph is going to be a positive shape. Okay, so we're just putting that there so that at the end, once we've sketched this graph, we can just go back and say, okay, yes, it's the correct shape. Okay, so step 1, we're establishing our shape. Step 2. Let's work out in step 2 what our y-intercept is. Remember, with any function, when you're working out a y-intercept, we say let x equal 0. So if I take my f of x equation, f of x, which is equal to 2x cubed minus 6x minus 4, and we are going to let x equal 0. That's what we are doing to work out our y-intercept. So therefore what we've got is f of 0 is equal to 2 times 0 cubed minus 6 times 0 minus 4, and we land up with a y-intercept of negative 4. Okay, so step 1 and step 2 are relatively straightforward. Step 3. Okay, step 3, What we are going to do now is we're going to work out the x-intercept. So just like we did with the y-intercept, we said let x equal 0. To work out the x-intercept, we're going to say let y equal 0. So to work out our x-intercept, we are letting y equal 0. Now that gives us a sum that looks like this. 0 is equal to 2x cubed minus 6x minus 4. Okay? When we are solving a question like this, one of the first things please to always look out for, it might not always be there, but it's worth having a look for, is a highest common factor. Okay? If it's there, it makes your life a lot easier to take it out and get rid of it so that when we're factorizing it, we're not dealing with such big numbers. And in this case, I hope you guys all can see that we do have a highest common factor, which is going to come out, and that is going to be your 2. So we're left with x cubed minus 6x minus, no, let's just clear that. We're taking out our 2. We've got x cubed minus 3x minus 2. Okay, and because your left-hand side is equal to 0, we are able to, essentially, if I divided both sides by 2, you would land up with just 0 being equal to x cubed minus 3x minus 2. Okay. Right, now we're sitting with a bit of a challenge because we now need to factorize this cubic equation or this cubic expression, and we need to now figure a way of how to do it. Okay. What we can do, first of all, a method one can use is your calculator. If you're sitting with a calculator that you actually have the function on it that you're able to calculate the x-intercepts of your cubic equation, that is one way of going about it. However, there are other methods that we can use, and I'm going to show you 2 of them, okay? The one method is going to involve what we call the factor theorem. Okay. I'm sure we've heard of the factor theorem, and what we have to do with the factor theorem is we have to find a factor, a number that will go into this expression that's going to give us no remainders, okay? When we're choosing a number to substitute into our equation to determine if it's a factor or not, what you want to do, grade 12s, is look at this last value at the end there. Look at your constant term, and I've got a negative 2 over there. Whatever your factor is, here's a little tip. Whatever the factor is, it's got to be able to go into 2. So now that obviously leaves me with 2 options. I've got a 1 or a 2 that I can either work with. So normally, once again, this is kind of just a general thing, is that if you're working with an even number such as 2, normally when we sub 2 into our equation to see if it's a factor, we have a pretty good chance of it working. Okay, so what we are going to do is we are going to substitute f of 2 into my equation, and we're going to see if we land up with 0. So I've got 3 times 2 minus 2. That's going to give me 8. So I've got minus 6 and minus 2, and there we go. We land up with 0. So what we have just established is that I've got a factor. Okay, now if x equals 2 gives us a value of 0 over there, the deduction we can make is that the bracket of x minus 2 is a factor. Okay, so this is the idea, grade 12s. We've got this cubic equation. Because we've got an x cubed, you know that when we factorize it, we're going to have 3 brackets. Okay, that's definitely going to happen. And what we've now just managed to do by using that factor theorem is we've just found the first bracket. Okay, now what do we do with this first bracket is we need to now establish how many times would the bracket of x minus 2 go into the original function that we have. Okay, so let's see what we're going to do. I need to work out how many times will x minus 2 divide into the equation, which was x cubed minus 3x minus 2. Now you can see I'm leaving a space over there, and there's a reason for that. When we have a cubic equation like this, what we want to do is we want to have it written in descending powers of x, okay? I've got an x cubed, I've got an x, but the value that I'm missing in the middle is x squared, all right? So what I'm going to do is I am going to add in a 0x squared, okay? we're doing that in order to make sure that every value has its own place and that everyone is taken note of, okay, that we're not forgetting anybody out. So now that we've done that, let's see what method we're going to do to work out how many times x minus 2 goes into the cubic equation. And this first method that I'm going to talk about is what we call synthetic division. Okay, synthetic division is going to work like this. We're sitting with the equation x cubed plus 0x squared minus 3x minus 2. With synthetic division, this is what you are going to do. We are going to draw ourselves a divide house like so, but we're doing it upside down, okay? And what we're going to write inside that divide sum is we're going to put all the coefficients of each of the terms of your cubic expression. So coefficients, remember, are every value, everything that's in front of your variable. So if I've got x cubed, there's an invisible 1 in front of that. So therefore, I'm putting a 1 in my divide sum. The next coefficient of x squared is 0. So I'm just going to put the 0 in front of my x squared. The next coefficient is negative 3, so we're putting just the negative 3, and then the constant term at the end, which was negative 2, okay? We worked out earlier that x minus 2 is a factor, so we needed to establish how many times will x minus 2 go into our cubic expression. So what we're going to do is take our x minus 2. If we take it out of the bracket, it becomes positive 2, and we put our positive 2 outside the divide sum, okay? With synthetic division, I'm now going to draw a line underneath. I'm leaving a space because I'm going to be filling in values in there. And the first step is that we take the very first term and we write it down at the bottom there unchanged. Okay, so whatever that first term is, it comes down as is. The next step of synthetic division is I take my 2 that's sitting outside here and I multiply it by the 1 down below. So 2 times 1 is going to give me 2, and that's where I put it over there. I'm now sitting with a 0 plus a 2, and 0 plus 2 is just 2, okay? Now we start the process again. I take 2 from outside here, and I multiply it by my 2 over there. 2 times 2 is going to give me 4. I've got negative 3 plus a 4, which is going to leave me with positive 1. And again, start the process again. I take my 2 outside and I multiply it by my 1 over here. 2 times 1 gives me 2. And if I've got negative 2 and positive 2, I'm going to land up with a 0. Now what you want, grade 12s, is you always want a 0 over there, because this last term over here represents your remainder. And if something is a factor, there is no remainder. Okay, so what we've now got is we've got this term, which is a 1, and we're going to put an x squared behind that. I've got a 2, and we're going to put an x behind that, and I've got a plus 1, which I'm leaving as a constant term. Now if I took that quadratic formula and I factorized it, we've got x and we've got x. I've got 1 and 1, and I've got plus and plus. And let's not forget that the other factor that we worked out earlier was x minus 2. That's the other bracket that's going to be as part of our cubic equation. So that x plus 1 multiplied by x plus 1 multiplied by x minus 2 is now the cubic equation factorized, okay? And let's not forget that right in the very beginning we said that we're letting y equal 0. So we're letting y equal 0, and we've now managed to factorize this cubic expression. So as a result, we're going to land up solving for x. I've got x is equal to negative 1. I've got another x is equal to negative 1, and I've got x is equal to 2. This is going to later be an interesting point, okay? We're going to talk about that later when we get to actually sketching our graph. Okay, so grade 12s, in your whole working out process, finding the coordinates of finding your x-intercepts is that one involves a little bit of work if you're using a method like synthetic division where you're having to actually work it out. Okay, it's not difficult, you just have to know the method. Right, that was step 3. So step 4 is now to establish our stationary points. Okay, stationary points in calculus is another way of referring to your turning points, okay? The reason why we call it a stationary point, very briefly, is that if I had a cubic function, remember a derivative, to go back to the original meaning of a derivative, is the gradient of a tangent. Now if I were to take a tangent and I were to draw a tangent at your function at each of your turning points, what we could say about the gradient of your tangent at each one of those turning points is that your gradient is equal to 0. There is no rate of change at those two turning points. Therefore, when we are working with our stationary points, the theory then is to say, to work out our stationary points, we calculate our derivative and we make it equal to 0. Okay, so the derivative of our original function, let's just go back to it, was f of x was equal to 2x cubed minus 6x minus 4. Okay, that was our original function. The derivative of that is 6x squared minus 6, and what we do is we let that derivative equal 0. Okay, so what we can now do is, once again, there's a highest common factor of 6 that's going to be able to come out. Because this side is equal to 0, your 6 falls away. And I'm going to factorize this side here. So we're sitting with an x minus 1 and an x plus 1, a difference of 2 squares. Therefore, I'm getting two values for x here. I'm getting x is equal to 1 and I'm getting x is equal to negative 1. Okay, what have I just worked out? I've worked out the x coordinates of your turning point. Now remember, coordinates is always going to have an x value and a y value. So we're not done with the turning points just yet. We need to now take those x values, we're going to substitute them back into the original equation and work out what the y value is of each of those turning points. Okay, so we're first of all going to have to take f of, let's take the first x value, which is 1, and back into our original equation it's going to be 2. Instead of x, I'm substituting it with 1, so 2x cubed minus 6 times 1 minus 4, and we are landing up with a 2 minus 6 minus 4, and what are we getting there? We're getting negative 8. Okay, that's the one turning point. The other turning point, we're going to take f of negative 1, and we're going to substitute it into our equation. Let's just do it underneath here so we've got some space. I've got negative 1 cubed. I've got minus 6 times by negative 1 minus 4. That is going to now give us negative 2 plus 6 minus 4, and that lands up giving us 0. Okay, so what are the two coordinates of our turning points that we have got? My one coordinate, x is 1 and y is negative 8. And the other turning point is negative 1 and 0. Now let's just go back for 1 second to this point here where I mentioned that this had an interesting point. Okay? When you're working out your x-intercepts and you ever land up with two values, two x-intercepts that land up being the same value, all right? One thing you know about that x-intercept, grade 12, is that that x-intercept is now, you know that it's going to double up as a turning point, okay? So if ever there's an x-intercept that's being squared, there's two of them, basically we know that at that point on your x-axis, your graph is going to bounce off your x-axis because it's a turning point as well as an x-intercept. So just something to bear in mind when you're doing your graph work, okay? It quite often comes up. Right, so we're on to the last step over here now, which is our step, I think we've said step 4, we're on to step 5, and that is going to work out our point of inclination. Point of inflection, sorry. Okay, point of inflection is just the point on your graph where your graph changes from being concave up to concave down, okay? Where the gradient of your tangent will change from always being a positive gradient to becoming a negative gradient, okay? So the way we calculate our point of inflection is we actually take our second derivative, okay? And we let that second derivative equal to 0. Let's just quickly go back. Our first derivative, if we remember, was 6x squared minus 6. That was our first derivative. So if we find the second derivative, we literally just do the process again. I say 2 times 6, which is going to be 12, x, and the 6 falls away, so that's what we're left with over there. And we're going to let that derivative equal to 0. So 0 is equal to 12x. And if I divide by 12, I land up with 0 being equal to x. So my point of inflection is going to be at 0. Once again, I need to know what the y-coordinate of that point of inflection is. So we take 0 and we sub it back into the original equation, all right? Subbing it back into the original equation, 2 0 cubed. I've got minus 6 times 0 minus 4, and we land up with negative 4. So we've got a point of inflection, which is at the point of 0 and negative 4. Okay. Right, we've done a lot of working out so far. We've worked out the shape of our graph. We've got the y-intercept, which we said was negative 4. I've got the x-intercepts, which work out as negative 1, and positive, what did we say? I need to remember, and positive 2. So negative 1 and positive 2, those are our two x-intercepts. We then calculated our stationary points, and the stationary points worked out at 1 and negative 8, and negative 1 and 0. And our point of inflection, which is 0 and 4. So we are ready now to sketch our curve. So we're going to draw ourselves an x and a y axis. We're going to make sure that we label everything. So we're going to call our x-axis and our y-axis. Okay. We knew that we had negative 1, which was an x-intercept, and we said we had positive 2, which was an x-intercept. Negative 4 was my y-intercept. I had negative 4 and 0. Okay, so those are all my x-intercepts for now. Let's have a look at our turning points. It might be worth just doing them in a different color so that when you're drawing it, you know which one's an x-intercept and which one's a turning point. Okay, we said that we had a turning point at, let's just make sure we got it, negative 1 and 0, 1 and negative 8. So negative 1 and 0. So I'm going to put a pink dot there just so I know that that's a turning point. And I've also got, now what I'm going to have to do is extend this line slightly because it's going to be lower down. Okay. Okay, so let's say at negative 8, let's mark it over here, is going to be at positive 1 and negative 8, and that's going to be my other turning points. Okay. Right, so we've got x-intercepts, y-intercepts, turning point, and the last thing we have to plot is our point of inflection, which we said was x was 0 and y was negative 4, which is going to be that point as well. Right, the shape, going right back to the very beginning, grade 12s, if we just flip back to where we were, was this. We had to start as an increasing graph, it then had to turn around and be decreasing, and at the next turning point, it then had to continue being increasing. So that's the shape we know we've got to take here. So my graph is going to start by increasing. It's going to get to the turning point, and it's obviously going to have to turn around. It's going to have to come down through your y-intercept and to your turning point. When that point, it's going to turn around again, and it will continue then as an increasing graph. We make sure that we label this carefully, so we make sure we call this our f of x function. And just make sure you're always labeling your coordinate points. We're not leaving anyone guessing as to what our coordinate points are, and that everything is clearly labeled. And that, I think, is going to be everything that we have to do. Right, so that then, after all that working out, is your cubic function. Okay, so you can see why it's worth a lot of marks. You can see what there's a lot of working out that's involved there. But as I said in the beginning, if you break it down into your steps and you just deal with it one step at a time, drawing these graphs is not difficult, and it's easy enough to get those 12, 13, sometimes 14 marks for sketching these graphs. Right, grade 12s. We're going to take a very short ad break. I want you guys to take a moment to think about that, because when we come back, what we're going to do is now take a graph and interpret a whole lot of information off that. So we'll see you after the break. Right, welcome back, grade 12s. I hope you guys had a moment to think about all of that, just to process all of it. And now let's have a look at the other way of looking at a functions question in calculus, where they've actually given us the picture and we have to interpret information from it. Okay, let's have a look at this question 2 over here, and let's have a look at what they are asking of us. They've told us that the function of f of x is equal to negative 2x cubed plus ax squared plus bx plus c. So obviously what we can see straight away is that they haven't actually given us the full equation. And they've told us that the turning points are t, which is 2 and negative 9, and s, which is 5 and 18. And this is what the picture looks like. Okay, so we've got ourselves a cubic graph that looks like this. And what we know as it stands is that our equation is f of x is equal to negative 2x cubed plus ax squared plus bx plus c. Okay. Grade 12s, when you are actually having to find the equation of the cubic graph from the picture, okay, it's important to start off by asking yourself, what is the information on the graph that you have been given? Have you been given the x-intercepts of the function, or have you been given the turning points? That's typically the two types of ways it will be presented to you. Just quickly, if you have been given the 3 x-intercepts, so just as a very quick picture, just to give you the idea, if let's say I've been given the 3 x-intercepts where let's say for instance I've got a negative 4, I've got a 0 and I've got a 5, the way you need to start that, the way you go about finding the equation of that, the equation of that function is you start by saying f of x is equal to a, and we have 3 brackets where I take x minus x1, x minus x2 multiplied by x minus x3, x3. The x1, x2, and x3 represent the 3 x-intercepts. So into x1 you would sub the negative 4, into x2 you would sub your 0, and into x3 you would sub your 5. And from there you would go about putting the equation together. Okay, that's if you have got the x-intercepts. However, in this equation, that is not what they have given us. What they've given us is the turning point. So there's a different way of approaching that. So let's get rid of this over here. And we are going to decide how we're going to use the information of having the turning points to find the equation. Okay. The first thing that jumps to my mind with second I see turning points is stationary points. And stationary points imply that you've got your derivative, which is equal to 0. Okay. So we now have to use that to help us find the equation of this function. Let's work out what the derivative is. And we are going to make it equal to 0. So let's just give ourselves some space here. So the derivative is going to be f dash x is going to be equal to, I'm going to land up with negative 6 x squared. I'm going to land up with 2 ax and plus b. The x falls away, and remember your constant term at the end falls away as well. So that's our derivative over there. And what we had was our 2 turning points. And remember we said that where the derivative is equal to 0 is your turning point. So this is what we're going to do. We're going to make the derivative equal to 0, and we're going to take each x coordinate in each of the turning points, and we're going to substitute them into the derivative equation. Let's see what that looks like. So my derivative is going to be made equal to 0. I'm going to use my first x coordinate of my turning point, which is 2, and I'm going to substitute that into the x's. So 2a, I've got a 2 plus b, and let's simplify that out. So I'm going to land up with negative 6 times 4, which is negative 24. I'm going to get a 4a plus b, and let's just get b on its own, which means I'm going to have positive 24 minus 4a is equal to b. I hope at this point, grade 12s, you can see where we're going with this. We're going to approach this, our approach we're going to take to this is a simultaneous equation, okay? It's not the only way we can go about doing this, but I think sometimes we know this method, we know how to approach it, so it's not a bad way to look at it. Okay, the next turning point we had was an x coordinate of 5. So we're going to do the same thing. We're going to take our derivative, make it equal to 0. But this time, into my x values, I'm going to substitute my 5. Okay. Right, so that leaves us with, I've got negative 6 times by 25. Let's just make sure I'm working out there. So negative 6 times by 25. That's going to give us negative 150. Negative 150. I'm going to have a 10a plus b. And once again, I'm going to do the same thing. I'm going to make b the subject of the equation. So therefore, equals to b. So if that was equation 1 and that was equation 2, the way I'm going to solve the simultaneous equation is I'm going to make equation 1 equal to equation 2. And that means I'm going to have 24 minus 4a in equation 1. And I'm going to make it equal to 150 minus 10a in equation 2. So what we've managed to do is eliminate the variable of b for now. We'll go back to it later, and we're now going to solve for a. Let's bring all our a's to the left and our whole numbers to the right. So I'm going to have a plus 10a. I've got 150, and that's going to be minus 24. We've got 6a. I've got 150 minus 24. Which is 126, 126, which if we divide by 6, we are going to land up with an a value of 21. Let's go back for a minute and have a look there. That's exactly what they wanted us to find. We wanted a equals 21, and we've done it. The next thing they're wanting us to do is prove that b is equal to negative 60. Now remember, with a simultaneous equation, once you've found the value of the one variable, take it and sub it back into either equation 1 or equation 2. It's not going to make a difference. So let's put it back into equation 1. That was 24 minus 4. Instead of my a, we know a is 21 now, and that's equal to b. So we've got 24 minus, and 4 times 21, that is going to give us 84 equals b. And 24 minus 84 is going to leave us with negative 60. Is that what they wanted from us? It is indeed. They wanted us to get negative 60 as our value for b. Okay, right, so the last thing we're now going to have to do is find our value for c. Let's just substitute in what we know at this point. I've got negative 2. This is my f of x function right now. F of x is equal to negative 2x cubed plus a. Now a was 21, so we've got plus 21x squared. I've got plus bx, but b was negative 60. And finally, I've got plus c. Okay, now the way to finally solve for this one last little variable here is that, remember, if you have got a point on your graph, whether it's a turning point or not, that point can always be substituted into the equation. Okay, it's always something that you have up your sleeve that you can use with graph interpretation, is subbing a point into the equation. So let's take our point 2 and negative 9 and let's plug it in and see what we have. The y would be negative 9, and everywhere we have an x, we're going to sub it with a 2. Okay, and let's see what we get. I've got negative 9. 8 times 2, that's going to give us negative 16. I've got 21 times 4, which is 84. I've got negative 120, and I've got c. Let's see what we've got here. So that would be 9. I've got plus 16. I've got minus 84, plus 120, and that's going to give us c. And if we work that all out, we're going to land up with, what did they want? 43. Let's see. So that's going to give us 43. I'm sure it does. Work it out on your calculators, grade 12s. Mine covers my work, so I'm battling to see it. So there we go. You're going to be able to work that out and get the c value of 43. And that gives us exactly what they were asking of us. We've proven all three values. And just a note on this grade 12s, when you have a question like this in your exam, one thing you mustn't do is if they ask you to prove that A is 21 and B is 60 and C is 43, a method, please, that you mustn't do is take each of those values and sub them into the equation straight away and try and prove a left-hand side equals a right-hand side. Unfortunately, we're not allowed to do that, okay? So you actually have to physically prove all three of the values by means of calculations. Okay, let's see now what the next thing is that they actually ask us on this graph interpretation. We're still looking at the same graph, okay? We've got the same picture over here. And it asks us to determine an equation of the tangent to the graph of f at x equals 1, okay? So if I were to estimate x being equal to 1 at about, let's assume let's assume, I don't know if it's 1 over there, we're taking a guess as to where it is, but anyway, the tangent to the graph, which is now going to go down like so. We're trying to calculate what is the equation of that line at the point where it touches your function at x equals 1. Okay, so what are we going to do? Grade 12's first things first, when we are working out the equation of a tangent, we are working with a straight line graph. Okay, a straight line graph, we are working with the equation y equals mx plus c. Okay, and let's go back to the very first thing we said about what is a derivative. A derivative is the gradient of your tangent, okay? So therefore, to calculate the gradient of my tangent, what we are going to need is the derivative, okay? So let's work out what the derivative of my function is going to be. Our original function, let's just quickly have it at hand here. We had negative 2x squared cubed. We had 21 x squared, I had minus 60x, and I had plus 43. Okay, the derivative of this is going to work out to be, I've got negative 6x squared, I'm going to have 42x minus 60, okay? And if that's the derivative, we are going to then substitute the point of contact between the tangent and your graph was at the point of x equals 1. So what we're going to do now with that 1 is take it and substitute it into the derivative, okay? So subbing it into the derivative, we are going to get, I've got negative 6, I'm going to substitute my 1 squared. I've got 42 times 1 minus 60, so negative 6 plus 42 minus 60. And let's see what that gives us. Negative 6 plus 42 minus 60. Negative 6 plus 42 minus 60. Negative 24. Okay, so that negative 24, once again, please don't forget, represents the gradient of your tangent. Okay, so as it stands right now, if I'm working with the y equals mx plus c formula, the m, the gradient, is now negative 24. The y-intercept, I don't know yet, okay? When we work with any point on a graph, if I have the x-coordinate, we are always able to work out the y-coordinate. And how we do it is we take the x value, and once again, we just sub it into the formula. So if x is equal to 1, if I were to plug that right back into the very original formula, to work out what the value of f of 1 is, I've got negative 2 times by 1 cubed. I've got 21 times by 1 squared. I've got 60 times by 1 plus 43, negative 2 plus 21 minus 60 plus 43. So negative 2 plus 21 minus 60 plus 43. Let's see. Negative 2 plus 21. Negative 2 plus 21. Now I've lost it. Minus 60 plus 43 minus 60 plus 43, and we get 2. Okay, so that means that I've got where x is equal to 1, the y coordinate at that point of contact is 2. Okay, so we're going to call that the point of contact between the tangent and the graph. Okay, so we're going to assume, so the point of contact between the tangent and the graph was at the point 1 and 2. So therefore, if that point is a point of contact, it's touching the tangent and it's touching the cubic function, so we can sub it in. So I'm going to substitute 2 into the y value. I'm going to substitute 1 into the x value. That's going to give me 26. I'm going to move it over. We're going to land up with 26 being equal to my c value. So what is the equation of my tangent? It's negative 24x plus 26. Okay, right, so that gives us the equation of the tangent. The last question they're asking us to look at of this particular function is the point of inflection. Now, we've already had a quick look at that. Point of inflection is a case of finding your second derivative and making your second derivative equal to 0. Okay, first derivative, let's go back for 1 second and just recall our first derivative, was negative x squared. We're over here. Negative x squared minus plus 42x minus 60. So negative x squared plus 42x minus 60. Negative x squared plus 42x plus 42x minus 60. That was my first derivative. So therefore my second derivative is going to be negative 12x plus 42. We then now have to take our second derivative and we make it equal to 0. So I'm going to make my second derivative equal to 0. So I've got 0 equals negative 12x plus 42. And when I move my 12 over, it's going to become positive 12x is equal to 42. When we divide by 12, we're going to land up with x being equal to 42 over 12. Okay, 6 will go into both of them, therefore 6 goes into 42 7 times, and into 12 it goes in twice. And that leaves us with an x coordinate, or an x value where your point of inflection is, of 3.5. And they didn't want the y coordinate at this point. If they did want it though, what we would do is take our x value and we would substitute it back into the original function. Okay. Right, grade 12s, we're going to take another short break. I want you guys to think about all of this, just take a moment to process all of it, and we'll see you after our break. Welcome back, guys. Right, let's go into the last part of the calculus application questions we're going to have a look at today. And this involves a bit of rate of change, okay? When we work with our calculus rate of change questions, we're still dealing with our derivative, we're still dealing with the concept of rate of change at a particular point. So all of those concepts still apply. We just got to make sure that we interpret what they're asking very carefully with a question such as this. Let's have a look at what they're asking us. They've said that water is flowing into a tank at a rate of 5 liters per minute. At the same time, water flows out the tank at a rate of k liters per minute. The volume in liters of water in the tank at time in t minutes is given by the formula Vt is equal to 100 minus 4t. Okay, so that formula represents how much water is in the tank at a particular time in minutes. Okay, so the first question is asking us what is the initial volume of water in the tank. So the initial volume of water in the tank would then assume that if we're looking at it in terms of a timeline, no time has passed if we're looking at it at the very initial time of the volume of the tank. So what we're going to substitute in is we are going to work out what the volume of our tank would be at 0 minutes. Okay, that's going to leave us with a volume of 100 liters. Okay, so therefore the initial volume of our tank is sitting at 100 liters of water. Okay, now we have to consider the water's running in and that water is running out, and how are we going to work with that? They've asked us now to write down 2 different expressions for the rate of change of the volume of water in the tank. The second they talk about rate of change, we are going to be working with our first derivative. Okay, rate of change, and particularly, as we've said, rate of change at a specific point is going to be your derivative. Okay, there's something quite interesting about the original function that they gave us over here. They said that v of t is equal to 100 minus 4t. This over here is a linear equation. Okay, that is linear, and the reason I know that is because I don't have any squares above my t value. So because I have a linear, because the volume is represented by a linear equation, what we know is that the rate of change is going to be constant, okay, because any linear function has got a constant rate of change. So if I were to work out the rate of change of this particular equation, if I were to work out the derivative of the function, we would just land up with negative 4, okay? And that's it. So no matter at what point in time we're talking about, it's going to be working at a rate of change of negative 4. But they asked me for 2 different ways of expressing it. Okay, let's go back and just have a look and see what the question said. We know that water is running into the tank at 5 liters per minute, but it's running out of the tank at k liters per minute. Okay, so essentially then the rate of change of how much water is in the tank is going to be represented by what's coming in minus what's going out. So the other way of representing our rate of change according to this information is to say 5 minus k. 5 liters coming in minus the k liters going out, and it's emptying at a rate of -4 liters per minute. Okay, so that would be the two ways of representing that data. Just remember, if they mention if there's a question like this and they mention rate of change, you're working with derivative and rate of change at a particular point. You then take that point and sub it into the derivative. Right, from there, they've then said to us, now they want us to determine the value of K. That's the rate at which the water is flowing out of the tank, okay? Well, let's just take what we've just worked out. We said that there were two ways of representing this rate of change, and the way we said was -4, which was the derivative, and we're going to make that equal to, because it's the same thing we're talking about, 5 minus K. Okay, so it's emptying at a rate of -4 liters per minute, and we've got 5 minus K, which was the other way of representing the rate. Okay, so if I now solve for K, what are we going to land up with? I'm going to bring K to my left-hand side to make it positive, and I'm going to land up with 5 plus 4 on the other side. And K equals 9. So if we think about this logically, it's coming in at 5 liters. If it was leaving at, if the water coming in was 5 liters per minute and the water flowing out was 9 liters per minute, because remember that's what K represented, then the difference between the two would be a difference of, there would be a drop in the water volume of 4 liters per minute, and hence the rate of -4. Okay, so that's what that question is asking of us, and actually in terms of the working out, not too difficult. But what is important, obviously, is just making sure that you understand what words mean in questions like this. When they're talking about velocity, if they're talking about rates of change, if they're talking about speed, they're talking about your derivative, okay? If they're talking about acceleration, what we need to know about that is that if we're trying to calculate acceleration, we work with our second derivative, okay? So go and practice questions like this. As I say, if you can pick up the words and what functions and what you're supposed to use with particular words, again, they're pretty easy to work out. Just got to read them carefully. Right, grade 12s, let's just go back to our checklist and see what we have covered. Okay, so we have sketched our cubic graph, and guys, again, it's just if you break it down into steps and you work through it carefully, it's a very manageable thing to do to get your marks in, okay? Finding the equation of, and obviously no, that's not the one. This one over here, interpreting your graph using principles of differentiation, finding the equation of your cubic graph. There are lots of different things that they can ask us with graph interpretation. However, you'll find that if you work through enough past papers, grade 12, you'll see that the questions they ask are fairly similar in nature. So they're going to ask you the same type of question, so go and do those past papers, all right? And we've had a quick look at rate of change, which didn't really, this particular example, involve maximum and minimum, but what we know about maximum and minimum, as in sort of working with our stationary points, anything to do with maximum or minimum, we're working with derivative equals 0, okay. This one over here, which is finding the derivative, or using the function of the derivative to answer questions about the function, okay. That one over there has got a bit of a interesting story to it, and in terms of our lesson today, we're not going to be able to cover that today. So what we're going to do in our live show is do an example of that just in detail, so you guys really get a chance to get a feel as to how we work through a question like that. So grade 12s, the moral of the story here is lots of practice. Once you get used to seeing the questions and you get used to understanding what it is that they're asking in calculus application, the questions start becoming very familiar and relatively easy to do. So I certainly hope that that has helped you with your calculus application, grade 12s, and I look forward to seeing you again next time. Study hard.